Okay, and welcome to the next lecture. Today we are going to dive a little deeper into the Colpitt's oscillator and concepts and chaos that are going to be kind of interesting, and hopefully I can demonstrate all of that to you as well as we talk through it. So what we're going to, as we have been discussing in the past, we've been looking at the Colpitt's oscillator and these items that we're going to be focusing on. We've talked about the background, we've talked about the characteristics, talked about the butterfly effect, or rather sensitivity to small changes, sometimes called perturbations. We're going to continue to talk about the Poincare surface, and then we'll do something, talk about controlling chaos, and hopefully show you a demonstration. Then I'm going to come back to synchronization. Going to come back to that, and we're going to put all that together. Even when we talk about controlling symbolic dynamics, then we're going to put that all together, and this is where this notion of synchrodyne amplification comes. And even if we have time for the rest of this lecture, the rest of this course, show you how some image processing techniques was derived from the utilization of chaotic oscillations, controlling symbolic dynamics, and the like. So could get interesting, but so I think really talking about some of the uses in chaos will kind of bring some of this home. Now, as you remember, this is the Colpitt's oscillator circuit. And what you would hope to get, at least the designers of this circuit would hope to get, as we look at time and let's just say Vc of t, you would hope to get nice pure sinusoidal oscillation of a single frequency, then that could be used to do other things. That was the hope. And if you tune these parameters, and that is the resistances, so that's here, this is where it lives in the equation. This resistance off of the emitter, that's where it lives here. The resistance of the inductor, which lives inside the inductor, actually, that's what RL kind of is. And, obviously the values of the capacitances, C, CE, and of course the inductor L. Those all have values that those are what we call parameters. So you see them in the equations, you see them in the circuit, you kind of get a sense of what the reality of all of this actually turns out being. Well, for certain values, and we've shared some of those values in the past when you utilized your MATLAB code and did some things with it, we show that this is a potential, right, of what you could get. Now, if, for example, you had just a single sinusoidal or some sort of, very simple oscillation, it would probably live in a loop like that, or some sort of additional periodicity, but always come back. So if you remember, we talked about how a fractal geometry was necessary for chaos to live and to continue to be chaos and not be periodicity. We talked about sensitivity to small perturbations. So this distance here between the starting point, call some delta start and the distance at the end point, at least where you stop checking, right? Let's just call it, E. Those are the Lyapunov exponent is related to the natural log of delta E over delta S. And you can see that if that is bigger, the delta E is bigger, which it will be if it's stretching, you're going to get a positive Lyapunov exponent, and a positive Lyapunov exponent indicates chaos if the system is bounded, because you could have that in an unbounded system that is just exponential. Okay, so these are the things we've established already. So now we want to start looking at analyzing these systems using the Poincare surface. And we discussed that last time, but I want to use a particular one, and you can, if you can see the dotted line, I'm going to draw over it a little bit just so you can see. It's a surface that cuts through this flow, and we're going to assume that it's moving in this direction, right? So it's going to come through here. It's going to pierce this surface and leave a point when it passes through. Okay? Same thing for all of these. So this surface is set up in constant I sub L. So let's say it's some value, say it's sitting right here. Constant, and I'll show you the exact numbers in a second. But it also is saying that here there's the line the surface starts here and is constant IL, and it runs through V sub E that way. It's going to run through V sub C, something like this. And of course, this projection is in IL, so you won't see the surface. But that's roughly what you are looking at. So again, as these points move through, they leave points on this surface as they pierce through. Now, what would that look like? Well, let's take a look. Here's the Poincare surface, and I'm going to do something while we're waiting. I'm going to run this code. I'll come back to this in a second, but I'm going to do a couple of things. All right, let's just do that. Let this run, and it's going to produce something so we can take a look at it. And because I like being able to move this stuff around and show you. Yeah. Okay, so here's the solution to the equations of motion for this system. I hope you can kind of see this dotted line where the Poincare surface is. And so as I'm moving this around, and you can do this on your own, you see where it's cutting through. So in VE, you go from a negative value to up to 3. So it's going negative, positive in that direction. But you can see how it, and you're feel free when you get your MATLAB code, I'm going to give this to you. You can do the same things. You see how it's moving through, as well as up and down in V sub C, which is the Z-axis. You can see that. The other thing that's nice about it, when you plant your cursor down, you can kind of see the actual points. So it tells you. So it's a constant 0.0075 amps. that's where that surface lies. Okay, so, but if you take a look at it, this is what it looks like as you're cutting through that surface. It's this arc that runs through, and each point that passes through is going to have another point later, right? And you can map that into what we call the return map. So here's the return map for VC. All right, so VC is this one, and it goes from, I have a range here from 9.6 to 11.4 volts. So if you look at that, here's the return map. This says that if I pierce the surface at this point, then I can tell where the next point will be. Now, how are we going to do that? Let's erect this line. So since this is the same scale, 9.6, 11.4, 9.6, 11.4, this is a square graph. So if I draw a line through from this point, and it's not going to be straight, but be the best I can, through there, you'll see that the fixed point lies just about 10 point, maybe 10.4, a little less than 10.4. Meaning that if you come through that point, it's going to want to stay there. It doesn't stay there, because if it did, it'd just be one period, so it moves away. But, so, you know, for example, now if I come in and let's use 10.5-ish, right? 10.5, then I know that when I go over here to the line and then project that onto the curve, that will be where my next point should be, and that is around 11.2. Then I'll go to 11.2 over here, and that'll tell me where my next one occurs. Now, this is not as simple as, remember in the logistic map, it was a single hump type map. This one has a couple of humps to it, which makes it a little bit more complicated, but you can still use it as the same way. Same thing with, if we looked at VE, and again, let's draw this line. And here's the fixed point here, which is roughly minus 0.25 or something like that, right? That's the fixed point for the V sub E curve. I'm going to make this bigger. V sub E n plus 1. This is V sub E n. Okay? Same thing with this one. I'll say VC sub n, VC of n plus 1. Okay? So the Poincare surface becomes almost like this sampling mechanism that allows you to sample points and get a sense of what's going on, and even is a useful tool. You could move this surface, you could put it where you wanted to, and there are some surfaces that are better than others. We could, erect a surface that is constant in this way, right? Like we showed, I think, in the last time. But we for the case of this exercise, we use this one. All right. So going further, here are those sample points that come off for the collector voltage. So this is VC again. Every time it crosses, these are the values that occur. Now you see it kind of wants to stick around here. The differences are smaller, but they do eventually grow pretty quickly, but they stick around the fixed point. See that? And same thing if you look at it for VE, it sticks around that fixed point. So how can we use the fixed point? Well, let's go a little further. So this is the fixed points in VC over here. And this is the fixed point, or this is the return map in VC, return map in VE. And here are the fixed point, you know, as you see, I know you can't really see these numbers too well right now, but when you get the slides, you can look at it. Around 10.4 and around minus 0.25. So, if these are fixed points, that if you could somehow keep this here, then you could control it and tease out the periodic orbits that live in the chaos. If you can keep them around those periodic points, you could control it. This was first introduced. This is this type of control, and we're going to go through the methodology here in a minute. But the researchers Edward Ott, Celso Grabogi, and Jim York from University of Maryland, which is my alma mater, and I actually got a chance to meet and work with these gentlemen. But this is sometimes called OGY control. And that's controlling periodic orbits. Now, what do? So the first thing to do is identify a region on the Poincaré surface for a periodic orbit. Now, as you remember, and this is the Poincaré surface again, here's VE, here's V sub C, and remember that these are the points that cross through the surface. As you recall, we said that the fixed point is roughly 0.25, minus 0.25 in VE, and roughly, and I didn't draw this line very well. Let me do that again. So it's probably more like right there, right? And kind of right there. So somewhere in the 10 point, roughly 10 point, my writing skills, roughly 10.4 volts, something like that, right? That's the fixed point. That's where it wants to be. That's where it wants to stay. Wait a minute, I did this wrong. I'm sorry. Hold on. Let's see why it didn't line up. Let me do this again. The point is actually minus 0.25, which is right here. Now that makes more sense. Now this lines up a little bit more with 10.4, which is what it's supposed to. So minus 0.25 and 10.4, roughly. Again, these are roughly. It's a little tilde. Okay? Those are the fixed points. So here's the procedure we're going to take. We're going to identify the region, which a region around the fixed point. We're going to calculate the distance between the crossing. So let's blow this box up and say that there are points, right, that fall in here, and say that this is the actual fixed point, and these are the points. So when it falls in this box or this window, then we say, what is the difference between it, then this is say VE, what is the difference between it and the actual fixed point? That's going to give us some delta value. I called it D here, but let's call it delta. So the actual point that crosses versus the fixed point. And then we're going to apply a perturbation that is some multiple of that distance. And we're going to use, let's use VC because that's a little wider. Same idea. I mean, the difference between this will be delta VC. Okay? So we're going to apply a pulse that is equivalent to a multiple of the difference in that. Now this M could be positive or negative depending on what we need, but let's go back to the circuit. I want to show you physically what that looks like, because you can actually, and we have done this with the actual physical circuit. So if I'm applying a voltage, I'm going to apply one right here and apply that VP right there, right to the circuit right there. So I'm going to measure the difference. I'm going to apply a pulse when it falls into place. Now we can simulate that, and we're going to simulate that. And the end result will look like something like this. And I'm going to show you with MATLAB why we didn't just trick it. We actually did it with these small pulses. As you can see right here, here's VP for over 500 or over 400 surface crossings. And these are the size of the pulses that were applied to tease out this particular circuit. This particular behavior. Now let's go to the to MATLAB, and I want to show you. Again, I'm going to post and give you these code, and you can take it and now. What I did was first I took a lot of those sub-programs and just put it in here so I could have one loop running. But I've established the Poincare surface. You can see here that it is at constant 0.0075 in that inductor current. And here are the other definitions of that Poincare surface window. The parameters, I used CP, the parameter 0, which, if you remember, I'll just pull them up. Here's the values of the parameters to give you a nice, decent chaotic flow. Now, this factor M, this is the multiplicative factor that I talked about. I made it 0 before so I could just run it, and it didn't apply the pulse. That's what I did a few minutes ago. But I'm gonna implement that. Now, again, this maximum window, I defined it to be 0.1. So that's the window around the fixed point. If it falls in that window, it'll apply the pulse. That's what it's doing. What else? Well, as you see in the loop, what happens, I'm integrating the equations as before. Apply the Poincare surface and a check for it. Now, if we get a positive surface crossing, then we get the surface points. That's what we did before. But now I say, if the difference falls within that maximum window I assigned, then create a pulse and call it M times the difference. And that's what's right here. Otherwise, make that pulse 0. And then I'm just keeping up with it right there so I can plot it later. Then this is just where all the graphs show up. Okay, so I'm going to turn back on the control by taking away this zeroing of this M factor and make that M factor 0.01. So when I run that, now, wait a minute. think I did something I shouldn't have. I might have made it too small. Let me make it a little bigger. There we go. All right. So the multiplier factor, the multiplier, I made it smaller. Now, as I made it bigger, and now you can see that it has teased out that periodic orbit, and it's trying to keep it around the fixed point. This is the control pulse amplitude, and what you can see is that the control pulses are roughly, 0.025 volts maximum, and minus, something even smaller, 0.007 maybe negative. And it's just kind of banging it around to keep it. Think about if I was trying to balance, I'm trying to balance this pin on my finger and it wants to fall, so if I'm adjusting the weight so that it doesn't fall one way or the other and keep it balanced, especially if there are forces that are trying to make it fall on either way, I have to, and of course if I try to do it even now, it's very, very touchy, So, but the point is I'm applying adjustments. So you kind of think of it like this: if you're applying these control pulses to keep it right around that periodic orbit. As you can see here, you probably can't see too much, but there's actually, so this is a period 3 that we controlled, and it is applying, as you can see, the surface crossing. There's a few surface crossings in 3 places. Here, here, and here. Okay, so that was a point gray surface in VC and VE. So that's how it works. Now, you can also take this and play with it. And even if I say apply a bigger pulse, I'm not sure what it's going to do. It's done some, looked like it's done some terrible things to the plot. Let me see. No. Nope. That's a PowerPoint. Hold on. Yeah, see, it actually deformed the oscillation, made it bigger, and so this you want to use very small perturbations, just enough to keep it there, but not too much to deform your system and do something different. Plus, you might want to conserve energy, right? So that's another thing. So let's go back and change it again, and this time I'm going to make it smaller. It was 0.1, but now I'm going to make it 0.05. See if we can still keep it where we need it to be. Okay, now this is interesting because you see it's a periodic orbit, but it's trying to become more chaotic because we don't have very firm control on it. So and that's because our control pulses are a little bit too small. And so we probably found a sweet spot was right around 0.1. The window that we're looking at, I think, is sufficient. So we don't really need to change anything on that. So I'm going to run it again and show you that it's controlled back to where it should be. All right. Now that's a very simple way to go about it. Let me go back here. Look at the point gray surface again. Because what happens is that for the fixed points, and let's go back to again where they were, we said that there was one they're here, and so at the 10.4 roughly, and at the minus 0.25, that is what we expect to find period 1. But there are other periods, that are all along this. Let's just say 3 and maybe period 10. Who knows, right? You could find them. And if you kept it coming back to that point at the right moments, then you could begin to control out other periodicities. Well, it even can get more sophisticated than that, and that's when I'll talk about symbolic dynamics and controlling symbolic dynamics. We'll talk about that at the next lecture. But what you can do here is remember that we talked about a procedure for control, and let's just review that. So identifying this window or region, getting a distance between the point you want it to pass through and the actual place it passes through, and determine a control pulse based upon that and some multiple that you can kind of feel out. There's actually a more elegant procedure to determine exactly, and that way you can optimize control, optimize how much energy or power you have to use to keep it under control. There's ways to do that, which I didn't get into. And then we're going to talk more about symbolic dynamics. We're going to talk about synchronization, and then we'll get more interesting. All right, so let's leave it there. I'm going to post this MATLAB code for you to play around with, and give you some exercises to work with accordingly, using that and seeing how sophisticated you can actually get without having to become an expert programmer in MATLAB. Okay, well that's it. So we'll take it from there. Thanks a lot for your attention, and I look forward to your questions and comments later on. Take care.